On this worksheet, we're going to be doing a few different types of aldol addition and condensation reactions. Here's that first molecule that we're looking at. Now remember that the first step of this, our base, the hydroxide, is going to abstract one of the alpha hydrogens. And we want to draw an enolate structure that has a lone pair of electrons on the alpha carbon. And I'm not going to draw the other hydrogen atom anymore in the structure, just to kind of make it easier to look at. That is going to attack a second version of the aldehyde, not the enolate, but the aldehyde. And the attack is going to happen at the carbonyl carbon, open up that carbon-oxygen double bond. And this is going to connect these two molecules together. So there is the aldehyde that was attacked. We open up the carbon-oxygen double bond, so there's a negative charge now up on that oxygen atom. We are making a bond between this carbon atom and this carbon atom right here. And it's actually kind of nice to number at least some of the carbon atoms. Kind of makes it a little bit easier to keep things straight. So I'm going to go through and put those numbers in, and I'm not numbering the way that we would number if we were naming it. And notice that I'm also using different numbers for the two different molecules, just trying to keep them straight. So in this step of the mechanism, we form a bond between carbon number 3 and carbon number 8. So that means that this right here is carbon number 3. Carbon number 3 has 2 and 1, and 2 has a methyl group attached, so it looks like that. And it also has carbon number 4, which is an aldehyde right there. And then after that, the water molecule that's created in this very first step is going to be used to protonate the O-. And that's going to look like this. And when we draw this, it's going to give us a chance to kind of straighten this molecule out a little bit, draw a little bit nicer. I'm going to go 5, 6, 7, 8 is now an OH, 3, 4. Like this, I'll fill those numbers in. 5, 6, 7, 8, 3, 4. Carbon number 6 has that methyl group on it. Carbon number 3 is also attached to 2 and carbon number 1. So we have this. This molecule here is the product of the aldol addition. Aldol addition reactions are also, or aldol, the products of an aldol addition reaction is also able to undergo a condensation reaction as long as there is another alpha hydrogen. So looking back at the carbonyl carbon, if there is another alpha hydrogen available, then it can undergo a condensation reaction. In this reaction, we are dehydrating, we're removing the OH group and also the alpha carbon and putting a double bond in that position right there. This is going to be done with the hydroxide ion that was created in this last step right here. That hydroxide ion is going to grab the alpha hydrogen. Carbon hydrogen electrons come in to make a double bond. OH group leaves. And we end up with this molecule right here. And then, you want to be careful of cis and trans isomers. I'm only going to draw this one just to kind of save space. And let's number those carbons to make sure that none of them were lost. Let's try our next example right here. Same kind of thing. So we want to begin by identifying our alpha hydrogen. First thing that's going to happen is that hydroxide is going to deprotonate the alpha hydrogen, and we're going to put the carbon hydrogen electrons onto the alpha carbon as a lone pair right there. That molecule is going to react with aldehyde number 2, not an enolate, but just a regular aldehyde. Lone pair of electrons are going to attack that carbonyl carbon and open up the carbon-oxygen double bond. I'm going to put some numbers on these carbons. When I'm numbering carbons in the aldol reaction, obviously, as you can see, I don't number all of the carbons. I just number enough of them that I feel like it's going to help me get this molecule correct. So I've numbered 3 and 4. This reaction, I'm going to create a bond between number 1 and number 4 right there. So that means I am creating a bond right here, and that is going to be carbon number 1. Carbon number 1 is part of a 6-membered ring right there, And carbon number 1 is also connected to carbon number 2, which is our aldehyde. Then we are going to protonate that O- using some water. And that's going to give me, this is number 3, this is 4, which is now an OH there. And there's a hydrogen on that. There's number 1 right here, which is also part of a ring. And that's connected to our aldehyde. Now, in order for this to be able to undergo condensation, there needs to be another alpha hydrogen. If we look at our carbonyl carbon and our alpha carbon, right here, we can see that there are no more hydrogens attached to our alpha carbon. So that means that this reaction stops at this particular product, can't undergo condensation. Now, here is what we would call a crossed Aldol reaction. A crossed Aldol reaction is between two different types of aldehydes. This means that we have a lot more products. This is asking us just to draw the possible products. We don't have to really show the whole entire mechanism. For a crossed aldol reaction, we want to consider the possibility that, like in this case, the molecule on the left is attacking the one on the right, or the other way around, the molecule on the right is attacking the one on the left. So that would give us two different products. There's also a possibility that this molecule will attack another version of itself, and this molecule would attack another version of itself. So we have, in theory, we have 4 different types of products that can be formed. Now, it's really difficult for me to just draw products of an aldol reaction without at least kind of drawing something that resembles a mechanism. So what I'm showing here is just sort of how I would approach the problem if I wasn't being asked to draw a mechanism. I would still use some curved arrows. I would still number my carbons just to kind of help me keep things straight. This is going to be my aldehyde that's getting attacked, 5, 6, 7. 5, 6, 7, and I am making this bond between carbon 2 and carbon 5. So there's my carbon number 2. Carbon number 2 has a 3 and a 4 attached right there, and carbon number 2 also has this aldehyde group. That's my carbon number 1. And then again, I'm not being asked to draw the mechanism of this, so what I'm going to do is say, okay, in the mechanism, that becomes an OH, so I'm just going to erase that that negative charge and make that an OH. And then the next thing that I'm going to do is just straighten this molecule out. Make it a little bit easier to look at. So here I'm starting with carbon number 1. I'm starting down here. This is going to be 1, 2, 5, 6, 7. 1, 2, which has 3 and 4. 3, 4. 5 has the OH group on it, and 6 has another methyl on it. So 5, 6, 7. And then also I want to recognize that I do still have another alpha hydrogen, which means that I can do a condensation reaction. That's going to put a double bond in between carbons 2 and 5. That's going to happen by the removal of the hydrogen and the OH on carbons 2 and 5. So here's one possible product. Now, a second possible product would be basically the attack in the other direction. So I'm gonna use the same numbers, 1, 2, 3, 4, 5, 6, 7. In this possibility, I'm having my enolate on carbon number 6, and it's carbon number 6 that will attack carbon number 1. So that is going to give me carbon number 1 is right here. When I draw these, I always draw in the product the molecule that was attacked first. There's 1, 2, 3, 4, and then in this reaction, I created the bond between carbon number 6 and carbon number 1. So that means that this is carbon number 6. Carbon number 6 has 7. It also has 5. So here's 5. Here's 7. 5 is the aldehyde group, and then it has this additional methyl group, which I have never numbered. So right there. And now, again, I'm going to redraw this, make it a little bit easier to look at. there's carbon number 5, 6, 7, and the random unnumbered methyl. 1, which has the OH. We're going to recognize that this becomes protonated. There's OH. 2, 3, 4. 2, 3, 4. In looking at this product, we want to ask ourselves if it can undergo condensation. Here's our carbonyl carbon, here's our alpha carbon, and this has no hydrogens on it, which means this is the product of the reaction, cannot undergo condensation. We're halfway done. We also want to consider the possibility that we get like a traditional aldol reaction. So we have two identical aldehydes reacting with each other like this. And so in this one, I'm going to make my enolate right here. I'm going to number these carbons, 1, 2, 3, 4, 5, 6, 7, 8. We'll get an attack like that. And in our product, here is carbon number 5, 6, 7, 8, 5, 6, 7, 8. The reaction forms a bond between carbon number 2 and carbon number 5. So that means here's carbon number 2, 3 and 4, 1, right there, 1 and 3 and 4. And then let's protonate that oxygen. I'm going to redraw this, see what it looks like. I'm going to start with the aldehyde. So that's my carbon number 1 to 2 to 5, which has the OH group on it. Here's 2, here's 5, and then I have 6, 7, 8, and I have 3, 4. 3, 4, and 6, 7, 8. Can this undergo a dehydration reaction or a condensation reaction? If we look at first find our carbonyl carbon, then find our alpha carbon. Are there any hydrogens on it? Yes, there are. That means we can do a dehydration right here, a condensation, and that's going to give us the same molecule, similar molecule with a double bond in between carbons 2 and 5. Now we still have one more to go. The last possibility would be this molecule reacting with another identical molecule. So that's going to be the last one we draw right here. And I just want to make sure I copied that correctly. Looks good. It's going to react with another version of itself. We want to pick either one of these to become the enolate. I'll pick the one on the left. We'll give that guy a negative charge, and the negative charge is going to attack the carbonyl carbon, open up the carbon-oxygen double bond. That's going to give us this molecule right here. We are forming a bond. I just cannot do this without my numbers. 5, 4, 5, 6. So we're forming a bond in between carbon 2 and carbon 4. There's our carbon 4. Here's our carbon 2. Carbon 2 is attached to number 1, which is an aldehyde, and also number 3 and a random carbon, a random methyl that I never numbered. Let's make this an OH and let's redraw it. There's carbon number 1, there's carbon number 2, it has number 3, and it has an unnumbered methyl on it. Here's carbon number 4, which has an OH. Here's 5, here's 6, there's another unnumbered methyl. This cannot undergo condensation because here's our alpha carbon. It doesn't have any hydrogens on it, so this is the product of this reaction. 4 different products of this particular reaction. Now what we're going to be looking at is kind of a retrosynthesis for an aldol reaction. We're shown a molecule that can be synthesized by an aldol reaction. And the question is, what aldehydes would we use to make this particular molecule? So we want to just kind of back ourselves up in this reaction, because here we're looking at a molecule that has undergone condensation. So that means that on one of these carbon atoms used to have an OH on it, and one of them used to have an H on it. And we want to try to imagine what that molecule used to look like. In this condensation step, we're removing an alpha hydrogen, which means the alpha position is the one that had the hydrogen on it, and then the other position is the one that had the OH group on it. So we've got this right here. This is what we're looking at. Then we want to back ourselves up even more in this reaction. We want to remember that in the prior to that, like immediately prior to that step, we had a deprotonated oxygen. So instead of an OH, it was an O minus, like that. And then we want to back ourselves up even more. We want to remember that this used to be a carbonyl group. So we want to kind of imagine that carbon-oxygen, the lone pair of electrons on the oxygen coming down and remaking that carbon-oxygen bond. Now, in order to put a double bond here, we're going to have to break a bond to this particular carbon atom. It's going to have too many bonds on it. Remember, there is also a hydrogen here. So we've got to break a bond. Which bond do we want to break? We want to break the bond that is going to separate the two oxygen atoms in this molecule from each other. So if we break this bond right here, we're going to end up with this chunk, and it's got both oxygen atoms in it, and that's not what we want to do. We're trying to get to two different aldehydes. So if we break this bond, we'd end up with this piece and this piece, two pieces that have the oxygens in them. So let's try that. We're going to move that bond down, and then we're going to break that particular carbon-carbon bond. And if we do that, we are going to get this molecule right here as an enolate, and we are going to get this molecule right here. Let me put some numbers on these carbons just to make them a little bit easier to see. 1, 2, 3, 4, 5, 6, 7. Here is 1, 2, 3, 4, and here is 5, 6, 7. This right here just is OH minus reacting with this aldehyde to give us the enolate, and also this step right here, a little bit of OH minus to give us the last product. We get to practice this one more time. Let's practice it right here. This one we're starting at the carbonyl and alcohol, so it's a little bit less to think about. So we want to remember that immediately prior to this molecule, we had an O minus. And then what we want to imagine next is that carbon-oxygen double bond. In order to make this carbon-oxygen double bond, we have to break one of the carbon-carbon bonds. Which one do we want to break? If we break this carbon-carbon bond, then we will end up with this segment and this segment right here. We're trying to separate these oxygens from each other, so we don't want to do that. If we break this bond, we will end up with this chunk and this chunk. Both the oxygen atoms are getting separated. That's definitely what we want to do. So we want to go like this, and we want to go like this. That's going to give us our oxygen atoms in two separate molecules. So we're going to have this guy right here, and we will have this guy right here. Let me put some numbers on these. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And this enolate is formed from this molecule with some OH minus. Here we have another problem. This is an intramolecular aldol reaction. So this is going to take place between a molecule that has two carbonyl groups. It's going to do the aldol reaction with itself. So to do this, we want to begin by identifying all of the different alpha hydrogens in this particular molecule. There's a lot of them. Any one of these alpha hydrogens could be removed and form an enolate. We've got all these different possibilities. So there's actually 3 different possible enolates that we could form. I'm just going to start by focusing on these alpha hydrogens right here. And notice this is just asking us to draw the products. We don't have to draw the full mechanism, although I am still going to kind of draw sort of a half of a mechanism to help me figure this problem out. So here's our negative charge, and it's going to attack this carbonyl carbon right here and open up that bond. That's going to make a ring. Now, in order to draw what this is going to look like over here, I'm definitely going to have to number my carbons. I'm going to number all of them, 1, 2, 3, 4, 5, 6, 7. But the ring is being formed with carbons 2, 3, 4, 5, and 6. That's a 5-membered ring. So I'm going to just begin by drawing a 5-membered ring, and I'm going to number 2, 3, 4, 5, and 6 on that ring. 2, 3, 4, 5, 6. The bond that I create in this is between carbon 2 and carbon 6. So that's the bond that's created right there. Carbon number 2 has number 1 attached, which is the aldehyde. So there's carbon number 1. And then carbon number 6 has an O-, and it also has carbon number 7, like that. So that looks pretty good. What we're going to do next is, first I'm going to just protonate that oxygen, and I don't like the way my 7 kind of looks like it's a hydrogen or something. So I'm going to do that. Now the next thing that we want to do is think about condensation. So in order to do this, we want to find our carbonyl carbon. We want to look at our alpha carbon. We want to ask ourselves whether or not there's a hydrogen on it. There is. And since there's a hydrogen on it, we can undergo a condensation reaction where we remove the hydrogen and the OH and we make a double bond. In this case, that double bond is going to go in between carbon 6 and carbon 2. So it's going to look like this. This is one possible product. Now we're going to consider a different possible product. I'm going to redraw this original molecule. I'm going to use the same numbers, 1, 2, 3, 4, 5, 6, 7. We've already considered putting the enolate on carbon number 2. We could also possibly have the enolate on carbon number 5. So that's what we're going to consider next. That enolate would attack carbon number 1. They're never going to attack the carbonyl carbon that's right next to them. They're always going to be attacking the other one. And if that were the case, that would also form a ring between 5, 4, 3, 2, and 1. So that's another 5-membered ring. So I'm going to draw that 5-membered ring, and I'm going to number that 5-membered ring. This 5-membered ring involves 1, 2, 3, 4, and 5. Carbon number 1 is the one that has the O- on it. That's the one that had the double bond open up. Carbon number 5, I think I'm going to have to scoot this over. Carbon number 5 has carbon number 6, which is a carbonyl carbon, and 7. 6 and 7. And then let's go ahead and protonate our oxygen right there. Can this undergo dehydration or condensation? Let's find our carbonyl carbon. Let's find our alpha carbon. It has a hydrogen on it, so we can do condensation right here. That would put a double bond in between carbons 1 and 5 right there. Give us this product, 7, 6, 5, 4, 3, 2, 1. We have one more to consider. Remember, there are 3 different possible places where we could have an enolate. 1, 2, 3, 4, 5, 6, 7. So the other possibility is that our enolate is all the way out here on carbon number 7. And in that situation, remember, they don't attack the carbonyl group next to them. They're going to attack the other carbonyl group all the way out there. And this would also give us a ring. This gives us a ring between carbons 1, 2, 3, 4, 5, 6, and 7. That would be a 7-membered ring. And what we know from these reactions is that they only work if they are forming a 5 or 6-membered ring. So a 7-membered ring means that we're going to get no reaction from this particular possibility. Again, this only works, the intramolecular only works if we form a 5-membered ring or a 6-membered ring, which are the most stable types of rings that we see.